Hi! Well, thanks for taking the practice exam. We're going to quickly go through the problems in a couple of minutes. But before we do, I just want to give a couple pieces of advice. This shouldn't surprise you. I often give advice. Occasionally it has been good. So, when you're taking the test, pay attention and read it carefully. There's a tendency sometimes to not pay attention, and you might notice that we maybe have a slightly different order that we write things in than normally, or maybe there's something which is a multiple selection problem and there might be more than one correct answer. Read the prompts carefully. Related to that is work to eliminate options. A multiple choice test is different than the kind of test we've done in the past. You don't have to show all your steps. You just have to do enough to be able to get to an answer. And one way to get to an answer is to say, well, let me eliminate other possibilities. And so if you can work to eliminate the other possibilities, that helps. There's a lot of time to take the test. We recommend you start early if possible and get it done. I know it looks like it says get it cloned, but that doesn't make any sense. No, get it done. And just don't have this hanging over you all day. You should just get it out of the way and be free. And don't panic. And I understand the test is stressful. That's why we want you to start it early. So if you need to take a break, get up from your computer and walk around for a couple minutes, you can do it. If you need to go scream into a pillow, get a drink of water, use the restroom, okay, that's fine. Don't panic. And remember, we do love you. Now, that isn't to say we're not going to challenge you, because we always challenge the people that we love. You might have experienced that in the last couple of weeks, that some of the biggest challenges have come from your loved ones. But we want you to succeed. We're not going to punish you. See, there's a difference between being challenged and being punished. We're here to challenge you. And that means that we believe in fairness. We're going to give you a fair test, and we're going to let you have an opportunity to demonstrate what you've learned. And we hope that you've learned something. All right. Well, with that out of the way, we can begin. Number 1. All right. And we'll try to go a little bit quickly. Our goal isn't to reteach the whole class. We're going to go through and do the problems, maybe highlight some strategies and things to watch out for. Okay. So, let C be the triangle oriented counterclockwise from 0, 0 to 1, 0 to 0, 1 and back again to 0, 0. Okay, so we can do a quick sketch. 0, 0 to 1, 0 to 0, 1, back to 0, 0. Okay, so yeah, that looks counterclockwise, good. By using Green's theorem, this integral can be written as which of the following? Okay, so we're really being tested on Green's theorem. So what does Green's theorem say? Well, it says, what? Well, if you have in general, I'll just draw the general case. Here's our region here, and here's our curve, which is the boundary of our region. The Green's theorem says that the integral over our region, well, let me start with the other side. The integral along the curve of m dx plus n dy is equal to the integral of our region of n sub x minus m sub y dA. So really we're being tested on, can we go from the line integral to this integral here? Now, seems pretty straightforward, right? What could be harder? So, okay, well, let's look at our region. So these are in terms of dx dy. So let's see, if we're thinking about this. Well, this is the line here, this line right here. Well, it's y equals 1 minus x, because you can see here, intercept at 1, slope of minus 1, or x equals 1 minus y. So, since our order of integration is dy dx, we say, all right, well, where does y go from? It goes from 0 to 1. Okay, well, they all agree on that part. Now, if I know where y goes from, where does x go from? Well, x goes from 0 to this curve, which is 1 minus y. So that says we can rule out the first two possibilities. That says you go to 0 to y. That would have been, if our shape had been more like that. Okay, all right. Well, which one of these do we need? 2x minus 2y, 2y minus 2x, or maybe neither one? Now we look at this and we say, x squared, y squared, and it's tempting to do what? Well, say, take rid of this with respect to x, and take rid of that with respect to y, you get 0. So you might think the answer is none of the above. And you can see that I'm really like, wow! But is that the answer? So, here's the thing. Be careful. Read the problems. Notice something here. See? It's something dy, something dx, in a slightly different order than what we're used to. So, this is really our m. That's really our n. So, it's going to be n sub x, which is 2x, minus m sub y, which is 2y. So, 2x minus 2y means our answer is C. So be careful. All right. You might think, that seems a little tricky. No. It's not being tricky. It's be patient. Don't rush. Take your time. Enjoy the test. Number 2. Evaluate the following line integral. So our curve is t squared t plus 1t, so that's our line. And we're going along the curve, xyz dx, half x squared z dy, half x squared y dz. Now, generally speaking, when we do line integrals, there's two things we can try. We can say, is it conservative? And is it not conservative? Now, the conservative has sort of a shortcut. The not conservative, well, you bite the bullet and you do it. How do you know if it's conservative? Well, let's try. The way we say we try is we say, all right, we're going to think of these as our partial derivatives of some function. So f sub x in front of the dx, f sub y in front of the dy, and f sub z in front of the dz. So integrate. In the first slide with respect to x, where you treat x as a variable, y and z as constants, 1/2 x squared yz. In the second slide, treat x and z as constants, y as your variable, integrate 1/2 x squared yz. Third slot, treat x and y as your constants, z as your variable, integrate 1/2 x squared yz. Notice we're getting the same thing, which means this is really the gradient of this function. All right, so what we've done is we've said we're integrating along our curve the gradient of 1/2 x squared yz. All right, so what happens next? Well, the nice thing is the theory says this is your potential function, namely that 1/2 x squared yz, evaluated between the endpoints. So where's our starting endpoint? That's that time t equals 0. So plug in 0. 0, 1, 0. Our ending endpoint at time t equals 1. 1, 2, 1. So we get 1/2 times 1 times 2 times 1. Okay? Subtract 1/2 times 0 times 1 times 0. Well, that's 0. 1/2 times 1 times 2 times 1 is 1. And we're done. Now, you might say, hey, couldn't I have done this the non-conservative way? Absolutely. So what would that look like? Well, you put a t squared here, a t plus 1 there, a t there. This would be a 2t dt, and, similarly work it all out. Would you get the same answer? Absolutely. Would you get the same credit? Yeah. But remember, you don't have to show your work, and so you should really focus on do it in an efficient way that gets you to the right answer. Don't be sloppy, but get to the right answer. That's the goal. Number 3. Let D be the solid with 1 less than or equal to x squared plus y squared plus z squared less than or equal to 4. And let S be the surface of D and N the outward pointing normal to D. Use the divergence theorem to find the integral on this surface minus 2z arctangent x 6y over pi z squared over 1 plus x squared dot n dsa. And this is not a multiple choice. This is a submit as a number rounded to the nearest hundredth. All right. Well, let's see what we get. So what do we have here? Well, first off, let's do the divergence theorem. So the divergence theorem says that the integral on a bounding surface of a solid of some function f, vector value function, dot n, is equal to the integral, triple integral, over our solid of the divergence of f, and that's, by the way, why we call it the divergence theorem, dv. So, that would be the integral over our solid. So now we go through term by term taking derivatives. In the first slot, take derivative with respect to x. So that's minus 2z over 1 plus x squared. Plus, second slot, take derivative with respect to y, 6 over pi. Third slot, take derivative with respect to z, 2z over 1 plus x squared dv. Whoops, ha. Remember, divergence we add. This is not a vector, it's a function. And if we've lived a good, clean life, good, healthy calculus lifestyle, nice things should happen. So, for example, those are constants. So what do we get? Well, that comes out 6 over pi, then the integral over our solid dv. So that's 6 over pi, and now what does that become? Well, if you integrate dv over your solid, what you get is you get the volume. So now we just have to figure out what the volume is. Well, what's our shape? It's a pair of spheres, right? So what happens is, if I think of x squared plus y squared plus z squared less than or equal to 4, well, that says I'm inside a sphere of radius 2. X squared plus y squared plus z squared greater than or equal to 1 says I'm outside a sphere of radius 1. So my shape is what's between two spheres. So I have this thing going on here, where I'm in between these two spheres. All right, so what can I do? I can take the bigger one, subtract the smaller one. So that will be what? Well, you have to remember the volume of a sphere. So that would be 4/3 pi, then r cubed, 2 cubed, minus 4/3 pi, 1 cubed. So from here, well, let's pull out the common thing. So we have 6 over pi, the 4/3 pi, and then we have 8 minus 1, so that's 7. The pi's cancel. 3 goes into 6 2 times. 2 times 4 is 8. 8 times 7 is 56. So our answer is 56. Now we need to submit our answer as a number rounded to the nearest hundredth. So we'll put in as 56.00. And there we go. There's our answer. Woohoo! We got it. Now you might say, wow, that's a nice answer. Well, of course, it's calculus. We always get lots of nice answers. But your question may have been, should we expect nice answers on this exam whenever we have to enter a number in? And yes, you should expect the answers to be nice when it's a number to be entered. And so be patient, and you can do it. You have the abilities. We know you can do it. All right. Number 4. If f of x, y, z is x squared sine of x in the I direction, plus y squared in the j direction, plus xy in the k direction, and s is the part of the paraboloid, z equals 1 minus x squared minus y squared above the xy plane, with upward pointing normals, what is the integral along our surface del cross f dot n dsa? All right. What to do? Well, actually, this can be not so bad. Now, what are some clues of what we should be doing? Notice that there's a curl here. Now, whenever you see a curl, that's sort of a clue that what you can do is you can use Stokes' theorem. So Stokes says what? It says that the integral on your surface del cross f dot n dsa is equal to the integral on the boundary of the surface. It's an oriented integral of just f dot t ds. All right, so that's how we can use it. But there's another option, which is called bring your own surface. In other words, use a better surface. So we can do that in this case here. So I like to oftentimes, if I can, bring my own surface. So let's think about our surface for right now. So initially, we have an upside down paraboloid. So all right, upside down paraboloid. So there's our z equals 1 minus x squared minus y squared. Now, let's think about what the boundary looks like. The boundary of our surface is this part right here in the xy plane. And it's the unit circle. That's our bound. All right. So now, if we're going to bring our own surface, then what we can do is we can say, let's find a better surface that has the same boundary. So we can modify our surface. And what does it become? Well, so we're still in three-dimensional space. We still have the same boundary. But now what we'll do is we'll make it just a flat disk. So there we go. There's our new surface. A nice flat disk. So the new surface corresponds to z equals 0. All right. That's good. Progress, right? Lots of good progress. So we're going to compute our integral, but now instead of s, let's call this a new surface. We'll call this p. I don't know. I needed a new name, right? So we'll say it's the integral along p of del cross f dot n dsa. All right. So this is a really great, beautiful surface. So let's take a second here and, well, but actually before I get too far down the rabbit hole, we should point out originally our normal vectors were upward pointing. Now our normal vector is 0, 0, 1. So what's going to happen is that I can replace n by 0, 0, 1. Which means when I'm taking the dot product, I don't care what happens in the first two entries of del cross f. So when it comes to del cross f, which that's our I, j, k, we have our partial x, partial y, partial z, and then our pieces here, x squared sine of x, y squared xy. Well, what we're going to get is we're going to get something, because we don't care what those somethings are, because they're going to dotted with 0. And then the last part, we're going to get what? Well, k, partial x of y squared, 0, right? Subtract partial y of x squared sine x, which is 0. So, what we have is that our integral over p becomes something 0 dot 0, 0, 1 dsa. Well, that's a great dot product. That says we're integrating over our surface 0. Well, that's one of the easiest integrals to do. Our answer is 0. All right, good. Now, of course, we're going to do it to the nearest hundredth. So I'll just go ahead and put 0.00. By the way, if you put in just 0, that's fine as well. But I'm just having fun. 0.00. See, I'm like channeling my inner engineer, which I never got to be. I'm adding digits of precision. Look how much more precise I am. There was 2 extra digits. It must be a better answer. Number 5. Consider the function f of xyz equals x cubed plus 2y squared plus az to the 5th, where a represents a constant. From the point 1, 1, 1, the rate of change of f is 5 in the direction, making an angle of pi thirds radians with the direction of greatest increase. All right, find a possible value for a. Well, that's interesting. All right, well, what do we have? Well, we have a couple of things going on here. There's a rate of change, and it's a direction. So we have sort of a directional derivative. So that's good for us to know. Okay, so let's talk about some things. So we have the directional derivative. And what we can say is that in general, the directional derivative is what? It's the gradient of the function at the point dot u, where u is our direction vector. Now, let's be careful here. Do we know what our direction vector is? And the answer is we actually don't know what our direction vector is. What do we know? It's good to figure out what we do know. This 1, 1, 1, that's our point P. All right? It's not a vector, it's a point. The only clue we have about our direction is this pi thirds. Now we can come back and say, oh, wait a second. When I'm doing a dot product, how do you do a dot product? Well, dot product, it's the magnitude of one vector, the magnitude of the other vector, and then the cosine of the angle between them. Well, it's a unit vector, so that's 1. So the cosine of the angle, that's cosine of pi thirds. Do we know what the cosine of pi thirds is? Well, yeah, that's a 60-degree angle. So if we were to mark this here, so 60 degrees, that says that this coordinate here is at 1/2 root 3/2, so that this entry right here is a half. All right. So what else do we have? Well, we know the value of the directional derivative is 5. So we've come to the following conclusion. So 5 is equal to 1/2 times the magnitude of the gradient of the function at P. Or we need the magnitude of our gradient to equal 10. Okay, so that's what we need. So as long as the magnitude of our gradient is 10, then it's going to be a true statement. So let's take our function. All right, what's the gradient of f? Well, take derivative with respect to x, 3x squared, derivative with respect to y, 4y, derivative with respect to z, 5az to the 4th. So the gradient of f at our point 1, 1, 1 would be 3, 4, 5a. So we can now say the magnitude of the gradient of f is the square root of 3 squared plus 4 squared plus 5a quantity squared. And we want that to be 10. Well, 3 squared plus 4 squared, that's really famous. 9 plus 16 is 25. So that's 25 plus, here, 25a squared equals 10 squared. So I'm just going to square both sides to get rid of the square root. Subtract 25. 25 times a squared is equal to 75. Divide. A squared equals 3. So what we come to the conclusion is that a is plus or minus the square root of 3. Okay, well, now notice it doesn't say find A. It says find a possible value for A, which means that there's two possibilities, or maybe more. It could be multiple possibilities. So we look through our list and say, are any of these either square root of 3 or negative square root of 3? Yeah, right there. Negative root 3. And that's one of our possible values for A. And we're done. Woohoo! Good. Number 6. What region results from applying the change of variables x equals u plus v over 2, y equals v, to the region bounded by 0 less than or equal to y less than or equal to 2, and y over 2 less than or equal to x less than or equal to y plus 4 over 2. Now this is a change of variables problem, and really this is really part of a Jacobian problem, so make sure you know how to do Jacobian problems, because these are important. This is the bounds part of the Jacobian problems, and make sure you can do the rest of the Jacobian problem as well. So, how are we going to proceed? Well, let's start by sketching our original region. So if I'm here in the xy plane, I'm told y equals 0 and y equals 2. So I can see, all right, y equals 0, y equals 2. And then what else do we have? Well, then we have these other bounds. So here I have y over 2 is less than or equal to x. So that's the same as saying that y is less than or equal to 2x. Right? Because I can just multiply both sides by 2. Now what is y equals 2x? Well, that's a fairly straightforward line. It goes through the origin, has a slope of 2. So here on this side, y equals 2x. And then what does this become? Well, this last part says y plus 4 is greater than or equal to 2x, or y is greater than or equal to 2x minus 4, which is if you took this line and shifted it down, and then were to go up this way. So this is the line y equals 2x minus 4. All right, so there we go. We've gotten a rough sketch of our region. So in particular, this is our original region. Now what I like to do is when I'm trying to figure out my new region is I just say, let me figure out what happens to each curve. Now some of these are pretty easy to spot. So for instance, y equals 0, y equals 2. I can convert those into our new shape and our new variables by saying, hey, these become v equals 0, v equals 2. So I need to have a v equals 0. That's good. That's working for all of these. And I need to have v equals 2. Well, that's good here. Oop, that's not working here. See, this is at v equals 1. So that one's out. V equals 2. That's fine. V equals 2. All right. So we've already knocked out one possibility. Now, how about these other lines? Well, how about y equals 2x? Well, what can we do? Well, if we think about it, I can think of it in the following way. I'll replace y by v, because y equals v, and I can replace x here by u plus v over 2. So what does that become? It says v equals 2u plus v. The v's cancel, so then we get u equals 0. Okay, so that says one of our shapes, our curves, has to look like that. Well, that knocks out d. That's not a possibility. All right, what about our last bounding curve? So what was that? Well, that was the curve y equals 2x minus 4. So again, replace y by v. 2 times u plus v over 2, and then minus 4. So we can get that v equals 2u plus v minus 4. The v's cancel. And so 2u has to equal 4, or u has to equal 2. So that says our last bounding curve is u equals 2. That knocks out this option, so our answer is A. That's our case, because we want v goes from 0 to 2, u goes from 0 to 2. This is sort of a, you might call this a skew transformation, so where we're just taking our curve and we're sort of, our region, and we're just slightly skewing it. And but there you go. There's your answer. And it's a little bit easier to describe this region. And that's one of our goals, of course, is we want to get things which are easier to describe. The big goal in calculus is now, and always has been, let's make life easier. Number 7. If we convert the surface described in Cartesian coordinates by x squared plus y squared equals 7x minus 5 into spherical coordinates, then the result is what? Okay, so we're going between coordinate systems. So we need to know a couple of basic rules. So they include x squared plus y squared plus z squared equals rho squared. Well, unfortunately, there's no z squared, so we can't use that one. We should also know that z equals rho cosine phi. R equals rho sine phi. Now, the other thing, this comes back to polar. R cosine theta is x. R sine theta is y. So let's figure things out. So x squared plus y squared, I didn't write that down, but I think you probably know that. That's r squared. So what we can do is we can sort of work our way up. So r squared, and x, I can replace that by r cosine theta. Now, what can I do with r? Everywhere I see an r, I can put rho sine phi, because r is not a spherical coordinate. R is cylindrical. So it becomes rho squared sine squared equals 7 rho sine times cosine theta minus 5. And now we sort of took 2 steps, and we now check to see, okay, which one matches? Well, probably rho squared sine squared. That's enough. See, this has this extra cosine. That's not going to work. This is missing the square. That's not going to work. They might say, hey, maybe you just divide everything by a sine phi, but the 5 didn't get divided by a sine phi, so that's why it's not C. So, but A, perfect. Rho squared sine squared phi, 7 rho sine phi cosine theta minus 5. You always have to be a little bit extra cautious whenever there's a trig function involved, because sometimes trig functions can do some interesting things because, well, you've got trig identities. So that means there's multiple ways to write things which are equivalent and correct. Number 8. Which of the following is a correct classification for a critical point of the function f of xy equals 2x squared plus 16x minus 4y squared plus 32y? Well, so first off, let's figure out where our critical point will be. There might be multiple ones. So f sub x would be, taking it with respect to x, 4x plus 16. We're going to set that equal to 0. Well, that's one we can solve. That's x equals negative 4. F sub y, well, that's minus 8y plus 32 equals 0. And again, that's one we can solve as well. That says y equals 4. So we're at negative 4 comma 4. Now that lets us rule out the last two, because that doesn't have negative 4, 4. So there's only one critical point. Now, unfortunately, there's still 2 options left, so we've got to push a little bit further. So let's see what we get. So we're going to look at our d, which is our fxx, fyy minus fxy squared. Fxx would be 4. Fyy is negative 8. And fxy is 0. That's negative 32, which is less than 0. All right, Now, here's where you got to be careful with your testing for classification. This is a second partials test, not a second derivative test. See, if it was a second derivative test in Calc 1, if you see a negative value, you think max. But here, when we see a negative value, we think not max, but saddle. So this is a saddle point. And therefore our correct answer is A. Wow, A is a popular choice. Interesting. All right. Number 9. Use the method of Lagrange multipliers to find the maximum value of y minus x, given that x squared plus 2xy plus 3y squared equals 3. Now, of course, it should be noted when it says use the method of Lagrange multipliers, it's really more of a suggestion. I mean, we can't really enforce that you use a certain method, so we're just going to see the answer. So it's probably a useful suggestion. Now, this is, again, one of these problems where it says, hey, let's submit our answer as a number. Ooh, no multiple choice for us. Or rather, infinitely many choices. What could it be? So, how does the procedure work? Well, you have your function you're optimizing and a constraint function. So this is our constraint function g. We want to set gradient of f equal lambda gradient of g. And our real goal here in doing this, so let's see, gradient, so f sub x minus 1 equals lambda. Take derivative with respect to x, 2x plus 2y. And f sub y is 1 equals lambda. Take derivative with respect to y. And we get 2x plus 6y. So our real goal in doing this is to really extract another relationship. You see, in some sense, we have too many relationships. There's this constraint, which has a relationship between x and y, and we're going to get one more. And that gives us two relationships, which should help us really narrow down our search. Well, when in doubt, solve for lambda. And I am a person who has doubt. It's one of the things I struggle with. So, divide by 2x plus 2y, and over here, divide by 2x plus 6y. Cross multiply, we get minus 2x plus 6y equals 2x plus 2y, or minus 2x minus 6y equals 2x plus 2y. Well, what to do from there? One thing we can do is we can move some terms around. So here we would get what? Minus 2x, and then another minus 2x makes minus 4x. Minus 6y will come across as a plus 6y. Minus 4x equals 8y. Or we could say x equals negative 2y. So that has given us a new relationship. Now, let's take that relationship and plug it into our other equation. So, everywhere I see an x, I'm going to put negative 2y. So, what do we have? Negative 2y squared plus 2 times negative 2y times y plus 3y squared equals 3. Or 4y squared minus 4y squared plus 3y squared equals 3. These cancel. We've lived a good life. You see, when problems start simplifying, that's a sign. You've lived a good, upstanding life. You've done a good job with your algebra. So, we get two possible values for y. Of course, once we know what our y is, that determines x, because remember, x is negative 2 times y. So, for example, negative 2 times negative 1 would give us a positive 2, and negative 2 times positive 1 would give us negative 2. So these are our locations. The maximins will occur here. Now, there is sort of the interesting sort of conundrum. Will it actually occur? Will it actually be the maximum? Yes, and that's a different story, but yes, this definitely has a maximum involved. All right, so here we go. Let's plug it in. So the function at negative 2 comma 1 would be y minus x. 1 minus minus 2 equals 3. The function at 2, negative 1. Y minus x minus 1 minus 2 is negative 3. Well, if we're looking for the max, well, I think 3 is bigger. So 3 is our answer. So we can enter it in as 3.0 0. Aha, good, done, nice. I like Lagrange multiplier problems, and I hope you do too. They're fun to do. All right. Number 10. If the plane y minus 2z equals negative 2 is tangent to our surface at 1, 0, 1, which of the following could be our surface? Wow. Okay, well, let's at least see if we can eliminate anything easily. So we have our 1, 0, 1. So how do we eliminate things easily? We just check, is 1, 0, 1 a point? So cosine 1 times sine of 0, that's 0, equals 0. Okay, that could be a point. We'll get here 1 plus 0 minus 1 plus 0 plus 1 minus 1. That in fact equals 0. Okay. How about this one? Square root of 2 times cosine of 0 times sine of 0. Still true. See, 0 equals 0 minus 0 plus 1 plus 7 minus 8. That's 0. 1 plus 1 equals 2. Wow. All of them go through the point 1, 0, 1. Okay, so there's no easy way to eliminate. So what's our next thing to do? Well, the next thing is to say the kind of surfaces we want are things where these are sort of our implicit surfaces. So we should clean these up a little bit. So for instance here, we'd have cosine of x, sine of y, minus z equals negative 1. Everything else, you get a constant. So what do we have here? This is going to be interesting. Well, now we're just going to work our way through. So notice here what's missing. There's no x. So really there's like a 0x. So that says the way that you do this, right, is you have your f of x, y, z equal to a constant c. So you're going to take your gradient of f and evaluate it at your point. That's going to be your normal. So one way we could proceed is just to see, well, do any of these have a nice normal vector? Well, they probably have. Some of them do, some of them don't. So we'll go through one by one. So the first one, well, derivative with respect to x, minus sine x, sine of y, and then derivative with respect to y, cosine x, cosine y, derivative with respect to z, minus 1. Now, plug in 1, 0, 1. Well, notice the sine of y, that's going to knock that out. That's 0. Then I have cosine of 1 times cosine 0, which is cosine of 1, and negative 1. Well, cosine 1 is a weird number. There's no way to get to that vector there. So, A is out. How about B? Okay, so that one would be what? 2x plus 3y. That's it for the x. Then 3x plus 2, that's it for the y. And minus 2z plus 1. Okay, plug in 1, 0, 1. We're going to get 2 plus 0, so that's 2. 3 plus 2, which is 5. And minus 2 plus 1, which is minus 1. Well, look, that's 2. There's no way to make that 0. So, B is out. All right, 2 down, 4 to go. Of course, it might be none of the above. And hey, you know, that happens sometime. I had a friend who I was helping him with his class one semester. He wrote an exam. And about 2/3 of the problem turned out to be none of the above because, you know, there were small mistakes. The answers were not quite right. So things can happen. All right, back to our problem. So square root of 2 cosine y. All right, sorry, taking derivatives here. Derivative with respect to x. Square root of 2 cosine y times cosine of x minus z. And actually, we can stop here, right? Because we're going to have something similar as what we had just up here. See how we had a 2 and said, no way that can happen? Cosine of y is cosine of 0. That's 1. Cosine of 0, that's 1. And then there's the square root of 2. All right. That can't be our answer. All right. Running out of options here. Okay. Man, it would be nice to go back to having to be a, right? Okay, next one. Derivative with respect to x. Well, there's minus 3y. Derivative with respect to y. Well, that's 2y minus 3x minus sine of y plus 7 e to the y. All right, how about derivative with respect to z? Minus 8. Okay, so plug it in. Minus 3y, 0. Then 2y is 0. Minus 3x, that's minus 3. Minus sine of y, 0. Plus 7. And minus 8. Minus 8. So what do we end up with? Well, that's 0. And then 4 and minus 8. Now, what's our normal vector supposed to be? Well, 0, 1, minus 2. Wait, does that work? Now, here's the thing you got to be careful about. Are these the same normal vector? Well, they're not the same vector. How do they differ? By a scaling factor of 4. But they point in the same direction. And therefore, in terms of the planes would be the same. So that will work. So there you go. Now how about this last one? We'll just do that one. You know, we're completists. We like to be done and get all of them. 2x, 0, 2z, and we see that the first entry, the first slot, will be a 2. So, in fact, this will be, the normal vector will be at 2, 0, 2. No, got to have a 0 in the first slot. All right, so we did find exactly one way to do it. Good, good. Now, at this point, you're probably thinking, these are hard. Well, I just want to assure you, we are giving you the better problems. When we had a choice between problems, we always said, let's put the ones which are more reasonable on the final. So you will find that the final is probably not so bad for some of these. So, good to know. All right. That's number 10. Number 11. What is the maximum rate of increase at the point 1, 2 on the surface z equals x to the fourth minus 4xy plus y to the fourth? Okay, so this is maximum rate of increase. So it's like we're trying to find the maximum derivative. You know, what's the largest it could be? So whenever you're looking for a maximum rate of increase, you say, hey, that's a gradient property. And in particular, what we're after is we're trying to get to the question, what's true about the gradient? So, in particular, the maximum rate of increase is the magnitude of your gradient at 1, 2. So, what's our gradient? Well, the gradient, so we're calling this z, it's really, we thought it was f of xy. So the gradient of f is 4x cubed minus 4y, comma, minus 4x plus 4y cubed. So the gradient of f at 1, 2 would be, when we plug in 1, for x we get 4 times 1 minus 4 times 2. So that's 4 minus 8. So that's negative 4, comma. Then we get negative 4 plus 4 times 8, 2 cubed. That's 28. So the magnitude of the gradient at 1, 2 would be the square root of negative 4 squared is 16 plus 28 squared, which is, we don't have to simplify. It's here. See? 16 plus 28 squared. Good. After that last one, we needed a breather. A chance to sort of like, catch our breath. Okay. Number 12. Which of the following represent the tangent line to the surface 2z minus e to the xyz equals 3 at the point 1, 0, 2? And we want to select all that apply. So actually we're probably pretty good at this after one of our recent problems. So let's see. We have, this is our f of xyz equals 3. So what do we have? Gradient of f, well, that'll be take the derivative with respect to x. Here, there's only a single x, so the first term goes away. The yz comes down because those are our constants. So minus yz e to the xyz. And then derivative with respect to y is going to be similar, but now it's the xz that comes down, so minus xz e to the xyz. And then the last one is going to have a 2 minus xy e to the xyz. Now we plug in our point 1, 0, 2. What do we get? Well, notice there's a 0 here. So any place where there's a multiplication by y is going to automatically be involved with a 0. So we get a couple of things. The first slot is going to be 0. Then this e to the 0 is 1, so minus x times z, so that's minus 2. There's a 0 here, so that's 0, so then there's a positive 2. And so that's our normal vector. So our plane looks like 0x minus 2y plus 2z equals, plug in your point, 1, 0, 2, well, you'd end up with a 0, 0, 4. All right, so there you go. Minus 2y plus 2z equals 4. Well, is that on our list? No. Well, wait a second, we could just simplify, right? So for instance, if I divide by 2, minus y plus z equals 2. That's the same as z minus y equals 2. Aha! That's the answer. But wait, did you see what I saw? There was a comment. Select all that apply. What does that mean? Maybe there's more than one surface. Well, no, there can't be. If there's a tangent plane, there's only one of them. So how could we have more than one? Well, let's think. Is there anything else that it might be? So we look through our list. Certainly it can't have the x involved because it should be 0x. And then, all right, can't have that involved. What about A? A looks now suspicious to us. So how do I get from minus y plus z equals 2? Can I get from this expression to 3y minus 3z equals negative 6? Well, what do you have to scale minus y by to get to 3y? The answer is negative 3. So 3y minus 3z equals negative 6. It turns out both A and D are correct answers in that these are equivalent planes. Ooh, sneaky, sneaky. All right. Well, good to see that now. Fool us once, shame on you. Fool us twice, it's not nice to fool people. At time t equals 0, a particle begins at rest at the point 0, 1, 0 and has an acceleration. And our acceleration is 4 negative cosine of t and negative 1 over t plus 1 squared. And our goal is find the particle's position at time t equals 1. All right, so what do we get? Well, we have a couple of things here we got to figure out. First off, we have an initial location, but we also are told at rest. Now, when something's at rest, that means that the velocity at time 0 is 0. So we know what the velocity looks like. So if we're looking for particle's position, we want to get to the position function. So let's start by saying, all right, we're going to work our way up. We know the acceleration, 4 negative cosine t, and minus 1 over t plus 1 squared. I'm going to write that for right now as minus t plus 1 to the minus 2 power. I think that's going to be easier to work with. Integrate. Term by term. Integral of 4t. Integral of minus cosine t. Well, integral of minus cosine is minus sine, so we've got to be careful. And the integral of minus t plus 1 squared, that's minus t plus 1 to the power minus 1 divided by minus 1. All right, did I forget anything? And what did I forget? I forgot my constants. All right, I'll just add them on. There's a constant vector. That works. So let's make some simplifications here. Minus minus makes that a plus. So we have that v of 0 is 4 times 0 is 0. Sine of 0 is 0. This will be 0 plus 1 to the minus 1, which is 1 over 1, which is 1, plus c d e, and that has to equal 0, 0, 0. So 0 plus c produces 0, so that says c equals 0. 0 plus d produces 0, so that says d equals 0. And then we have 1 plus e gets to 0, so e has to equal negative 1. So our real function for our velocity is 4t minus sine t, and then 1 over t plus 1 minus 1. All right, so one more time. So the position, well, we'll call it r of t. Integral of 4t would be 2t squared. I'll throw the constants now on the inside here, so I'll use a capital F. Working our way through the alphabet, right? C, D, E. Next comes F. Integral of negative sine is positive cosine. So cosine t plus some constant g. Integral of 1 over t plus 1, that's log of t plus 1. I suspected I'd have a log in the answer because there's a log here. And then minus t plus h. Again, we know where we're at time 0. So we get that r of 0. Well, plug in 0 plus f is f. Cosine of 0 is 1 plus g. Then log of 1 minus 0 plus h is h. And that's going to be equal to 0, 1, 0. Well, notice that says that f is 0, h is 0, but also it says g is 0 because I already have a 1. So our position function will be 2t squared plus capital F cosine of t plus capital G. Why am I was copying the constants down again. I don't need to copy the constants. We saw that the constants were 0. 2t squared cosine of t log of t plus 1 minus t. All right, what's our last thing to do? Plug in 1. So r of 1 is, that's a really thick one, 2 times 1 cosine of 1 log of 2 minus 1. And we scan and we see, aha, A. A is the correct answer. Number 14. The surface defined by the equation y squared equals 10 minus z is best described as a cylinder, elliptic paraboloid, hyperboloid of one sheet, hyperboloid of two sheets, or hyperbolic paraboloid. Well, that's, how do we think of that? We can actually sketch this surface. It's not such a bad one to sketch. Normally, we would probably write this in the form z equals 10 minus y squared. So if I'm thinking about this in the yz plane, it's an upside down parabola. Now that's in the yz plane. So what's going to happen is it's going to be this parabola just shifted along. All right. So, it's some sort of parabola moved along. I see the words parabola showing up. That sounds very tempting. Very, very tempting. So tempting, I'm not going to take the bait. Why? Be careful. Because what do you notice about this equation? there's no x. Now, when there's not an x involved, what that means is that you're just getting copies back and forth. And we actually had a word for that. That's a cylinder. So whenever there's a missing variable, we call that a cylinder. So that's one thing to keep in mind. Now, why is it not an elliptic paraboloid? An elliptic paraboloid would be a bowl shape. See, this is not a bowl. It doesn't ever come up on one side. The hyperbolic paraboloid has a better name. We've actually seen it already. It's the saddle. So that's a hyperbolic paraboloid. And again, there's movement going in multiple directions, whereas that doesn't happen with cylinders. So, missing variable, that's a cylinder. All right. Number 15. For a function z of xy that satisfies an implicit relationship, namely x e to the yz minus y e to the xz plus z equals 0, find the derivative of z with respect to x at 1 log 2. Now, how does this work? Well, what we do is we imagine, I'm going to think of z as being a function of x, y. So that's how we're thinking in our mind. And now we're going to take the derivative of everything with respect to x. So I'm going to come up here and I ask the question, where does x show up? Well, I claim it shows up in a couple of places. It shows up here where there's an x and here where there's an x. But that's not all. It also is going to be here, there, and there. Why? Because I'm going to think of the z as containing something about x. So, I have lots of things. So, here, let's be careful. Product rule. Derivative of the first is 1 times the second, e to the yz, plus the first times the derivative of e to the yz. So, chain rule. Y is a constant. So when it comes down, y, derivative of z with respect to x is partial z, partial x. Y is a constant, e to the x, z. Now, here, I have to do a product rule. Well, derivative of x is 1 times z plus x, partial z, partial x. Now, last term, the z, that's partial z, partial x. Okay, at this stage, we're looking for what happens at a very particular point, 1 log 2. So I'm going to go ahead and I'm going to now evaluate right away. So evaluate at 1 log 2. So what do we get? We're going to get e to the log 2, which is known as 2, plus 1 times e to the log 2 times 1, so plus 2, partial z, partial x, minus 1 times e to the x z, well, that's again e to the log 2, so minus 2, then what do we have? We have a log 2, which is z, plus partial z, partial x, plus partial z, partial x equals 0. Now, nice things should happen to us. If we've lived a good, clean life, beautiful things should happen. Notice there's a 2 partial z, partial x. There's also a minus 2 partial z, partial x. So those terms will end up canceling. And then we're only left with a single partial z, partial x. So we have that partial z, partial x. Well, let's move the other things across. There's a minus 2 log 2, which moves across as a plus 2 log 2. And then there's a 2 at the beginning, which moves across as a minus 2. So 2 log 2, minus 2, aha! A. Wow. A popular choice. Now, you're probably thinking, I should probably always guess A. No. We're on to you. We're on to you. We're going to make the final mix up a little bit. Maybe it's going to be B. All right. We'll see. We'll see. Number 16. Find the mass of the plate in the shape of the region formed by the inside of the cardioid, r equals 1 plus sine theta, and outside the circle, r equals 1, whose density is 1. Actually, this is not so bad. It's really almost a Calc 2 problem. But we just never really sat down and did it in Calc 2. Now, 1 plus sine theta, it has the sign of sort of an upside down heart. All right, so there's our 1 plus sine theta. And so it goes all the way up here, it goes up to 2. Here is at 1. Here is at 1. So again, it's distance from the origin. And outside the circle, r equals 1. So the circle r equals 1, you can see that this is kind of a weird picture. If I want to be inside the cardioid, but outside r equals 1, that says I'm really after this part right here. All right, so there's our region. So this, I'll label our region, we'll call it R. Now, how do you find mass? Mass is the integral over your region of density dA. Now, in our case, our density is really clean. Our density, where we were told, is 1. So this is 1. So really, it's the integral over our region dA. Now, how do we integrate that? Well, we've got to figure out our bounds. Well, we have some nice things going on. We clip here at 0 and pi. So remember, our dA is r dr d theta. I don't know why I'm giving myself space, because our density, remember, is just 1. Now, when we're thinking polar, and this goes a similar philosophy of polar and spherical, we always think, how do you come out from the center? So that's the key. Well, we're going to come out till we hit the first object, which is the circle, and then we go out till we hit the second, which is the cardioid. So we're going to go from 1 out to 1 plus sine theta. All right, so we get integral 0 to pi of r. Integral of r is 1/2 r squared. R equals 1. R equals 1 plus sine theta, d theta. I can pull the half out, so that's 1/2. And then we have integral 0 to pi of 1 plus sine theta squared minus 1 squared, d theta. So that would be 1/2 integral 0 to pi of 1 plus 2 sine theta plus sine squared theta minus 1, d theta. The 1's cancel. All right, good. Woohoo! We've lived a good life. Now, how do we handle the rest? Well, the 2 sine theta, that's pretty straightforward. The sine squared, how could we handle that? And the answer is power reduction. So we have 1/2 integral 0 to pi. Then the 2 sine theta, like I said, that's fine. Sine squared is 1/2 minus 1/2 sine of double the angle. All right, so what does that lead us to? Whoops, I'm running out of space. Okay, so this is really convoluted here, but all right, at the end we'll get our answer. So there's 1/2 from the front. Integral of 2 sine, well, that's minus 2 cosine. Integral of 1/2 is 1/2 theta. Integral of minus 1/2 sine 2 theta is, whoops, did I write sine? That's not power reduction, it's cosine. Okay, so it's going to be minus, integral of cosine is sine, 1/4, and integral of cosine is sine, so 1/4 sine of 2 theta. All right, evaluate from 0 to pi. Now we plug in pi, and hopefully we get some nice numbers. 1/2 Cosine of pi is minus 1. Minus 2 times minus 1 is positive 2. Plus pi over 2. And sine of 2 pi, 0. Good news for us. Now, when we plug in 0, sine of 0 is 0. 0 is 0. Cosine of 0 is 1, so minus 2. So, what is that? Well, minus and minus makes this really a plus. So what we have is 1/2 times 4 plus pi over 2. And, well, we can common denominator of 2, right? So that would be 8 plus pi over 2, but then there's another 2, so that's 8 plus pi over 4. So, C. Oh, boy. What a fun one. Good, clean fun. Good, clean fun. Don't get too hung up on the algebra and the arithmetic, the trig identities. That's not what we're going to be focusing on. We're really going to be focusing on, can you set things up and carry them out properly? So that's what we want. Make sure you can do that. All right. Number 17. Evaluate the integral by first reversing the order of integration. Well, that's probably a good strategy because we can't integrate it in the way it's been given to us. So we'd have to do reversing the order of integration even if they hadn't said to do it. So, all right, well, what's the idea? Well, if we sketch our region here, we're told x goes from 0 to 3, and then we're told y goes from x squared up to 9. So here's our y equals x squared, here's y equals 9. So this is our region, this sort of piece of a parabola. All right, so how do we do this? Well, we're going to flip our order. So integral, it's still the same function because you don't change the function when you change the order. You just, well, change the order. So we start saying, well, where does y go from? Well, y goes from 0 up to 9. 0 to 9. Where does x go from? Well, we say once we have a particular y value, we're going to move back and forth in the x direction. So we're going to start here at x equals 0. All right, that's not so far bad. We're going to come over here to x equals, be careful, see this is y equals something, we need x equals. So it'll become square root of y. All right, so now that's the reversing. We have to carry out the integral. So we have integral of 0 to 9, integral of x cubed, 1/4 x to the 4th. The e to the y cubed is a constant. We're going to evaluate that from x equals 0 to x equals root y dy. Now at 0, that's 0, good news for us. At root y to the 4th will become y squared. So 0 to 9, 1/4 y squared e to the y cubed. And now, previously e to the y cubed we were kind of stuck on, but with this new addition of a y squared, we can make progress. Let's let u equal y cubed. Then du would be 3y squared dy. I can move the 3 across, so we get 1/3. So, what does this become? Well, we're going to get a 1/4 times another 1/3, because that y squared dy becomes a 1/3. So that's a 1/12, that's the constant, I'll pull it out. Then we have e to the u du, and our bounds, 0 cubed is 0, 9 cubed is 729. Now you have a calculator, you can compute that out. It's not so hard to do 729. So 1/12 e to the u, evaluated from 0 to 729. So that's 1/12 times e to the 729, subtract e to the 0, which is 1. Good. Good. Woo! Wow. Fun stuff. Good problems. All right. Number 18. Let f of t equal t. It's sort of this strange notation. Looks like there's sort of, we call this the ceiling function. And what does that mean? Well, you want it to be the smallest number which is above t. So for instance, if we plug in pi is 3.14159. Well, we want to get a whole number. Like that's what an integer means, whole number. We say, well, what's the largest number just above 3.1415? It's 4. Okay, all right. Find the integral over our region, f of x plus y dx dy, where r is the rectangle. X goes from 0 to 2, y goes from 0 to 1. And we're going to submit the answer as a number, rounded to the nearest hundredth. Well, let's think about our function here. Now, sometimes when you look at this function, it's sometimes called a step function. Because if you look at what it looks like, so this is the ceiling of t. So at 0, well, it's 0. But if I go just a little bit past 0, it jumps up to 1. So it jumps up to 1, and up until 1, and then it does a jump again. So that's our ceiling function. All right. So that's what our function looks like. Now, how does it translate here in the xy plane? So our region, we have x goes 0 to 2, y goes 0 to 1. Now, one way to think about it is to say, well, let's think about sort of the interesting inputs. So the interesting inputs are when x plus y is a whole number. That would be the most interesting thing to look at. So, for example, if x plus y were equal to 1, what would that look like? Well, that would look like this. This is x plus y equals 1. How about x plus y equals 2? Well, it would look like this. This is our x plus y equals 2. How about x plus y equals 3? That would be here. And over here in the very corner, x plus y equals 0. Now, what's the story here? Well, what happens is we're creating the strips. We're taking our plane and we're doing little strips. So, in our strips, well, let's just talk about each one in between. So if I'm saying this first strip, what's happening? Well, it says x plus y is between 0 and 1. So that says where I'm plugging into my function f is between 0 and 1. So I'm going to jump up to 1. So I'm going to be equal to the value of 1 in that piece there. Now, if I move over a step, so in other words, I'm in this next strip here, what's going to happen is that I'm going to have x plus y will be between 1 and 2. Okay, so if you come here, what does that mean? Well, it means if I'm between 1 and 2, I'm going to jump up to 2. So my function is 2 on that piece. Well, what about my last part? X plus y equals 3. Well, that's this piece here. Now, what's going on there? Well, what's going on is that I'm between 2 and 3, and so when I think about my input, between 2 and 3, it's going to jump up to 3. So my function is 3. So what we can do is we can think of, if I want to integrate this function, I'll really think of it in 3 parts. There's this part right here where the function is 1. There's this piece right here where the function is 2. And there's this piece right here where the function is 3. So now each one of them, though, is really easy. So for instance, this first piece, well, it's the area, it's a triangle, 1/2, base height, so 1/2. The height of this coming up is 1, so area of the triangle times 1. For the second piece, it's a little bit more subtle, but you can actually kind of spot it. I can imagine cutting it into 2 triangles and put them together to get a 1 by 1 square. So the area is 1, the value of the function is 2. So I can think of it as like I'm integrating a constant 2 over that. So it's like twice the area. This is 1 times the area. This would be thrice the area. So in the last piece, what will happen is, again, it's a 1, 1, and it's a triangle, so the area is a half, and the value is 3. So we get a half plus 2 plus 3 halves. And if we add those together, let's see, a half plus 3 halves, 4 halves, which is 2 plus 2 more makes 4. All right, so there's our answer, 4. And accuracy, add in to the 100th, 4.00. Again, you could just plug in 4, but there you go. Number 19. A triangle has vertices at the points A, B, C in three-dimensional space. So here we go. A, B, C. So there's our triangle sitting there in three-dimensional space. Which of the following represents the area of the triangle? So what we have is we're after what's the area. Now, in some sense, what do we need to know? Well, the area, if I have two vectors here, u and v, then what happens is, if I were to extend it, the area of this parallelogram is the magnitude of u cross v. If I were to cut it in half, I can say that the area of a triangle would be 1/2, because it's half of the size. So I should be looking for something which has a half. So that rules out B and D. So they don't have a half involved. Now, let's look at the last three options. So here, there's a 1/2, AB, and AC. So yeah, that's a triangle. Okay, that's good. All right, how about this one? BC and BA. Well, yeah, that actually turns out to be good. All right, how about this one? AB and BC. Will that give us the area of the triangle? Now, what do you think? Yes or no? Well, you might say no, because we want the tails together coming out. Well, here's the thing. If I want to flip the direction, I multiply by a negative. Multiplying by a negative does what to the magnitude? Doesn't change it. So this will also give us the area of the triangle. So it turns out there's three possible answers. So we should probably say select all. Right? Multiple select. All right. All right, next problem. Ooh, projection. Find the projection of a vector u onto the vector v. So it might be helpful to remember the projection formula. Now the idea of projection, beautiful idea. What you're after is you're asking how much of this vector v points in that vector. Sorry, this vector u points in that vector v. So there's a nice formula. It says take u dot v over v dot v times it by v. You'll notice there's 4 v's, and it kind of feels like they cancel. They really don't, but it kind of feels that way. Now once you know the formula, the rest of it is just patience, right? So what do we have? Upstairs we're going to have minus 1, 3, 3, dot 2, minus 2, 1. And downstairs we're going to have 2, minus 2, 1, dot 2, minus 2, 1, times 2, minus 2, 1. So we're going to get minus 2, minus 6, plus 3, over 4, plus 4, plus 1. And that's multiplied by 2, negative 2, 1. Minus 2, minus 6, plus 3. Well, that's minus 8 plus 3, which is negative 5. 4 plus 4 plus 1, 9. And 2, negative 2, 1. All right, so that's our vector. Now, it looks like they've multiplied the scalar through, so we're going to do the same thing. Scalar multiplies through. Let's see. Negative 5 nines times 2, negative 10 nines. Negative 5 nines times negative 2, positive 10 nines. Negative 5/9 times 1 is negative 5/9. So, negative 10/9 in the first entry. Looks like it could be that. 10/9 negative 5. It is that. E. Woohoo! Nice. Nice. That was good. You know, occasionally you find a problem that's like, that wasn't so bad. And you kind of say, we should have more problems like that. Don't worry, there will be plenty of problems like that. All right. Number 21. This is, let's brace ourselves. And when you first see this, you might be like, partial credit. I miss you, partial credit. Well, that's okay. I'm sure partial credit misses you too. But you know, let's not panic, because panicking doesn't help. What do we need to do? We need to be methodical. The other thing is, and we're friends here, so I can tell you this, between me and you. When we were picking what problems should go on the final, we thought to ourselves, all right, let's pick the problems which are the more reasonable. So we didn't say, wow, this problem's too easy, let's not put it on the final. No. We definitely said, you know what, let's revisit. Let's make it a good experience so that students leave the final exam with a smile on their face, just the way they left a class throughout the semester. So we're doing a second order Taylor polynomial approximation at 1, 2. Now in general, that means we're going to take the function at 1, 2 plus f sub x at 1, 2 times x minus 1 plus f sub y at 1, 2 times y minus 2 plus fxx at 1, 2 times x minus 1 squared over 2 plus fxy at 1, 2 times x minus 1 y minus 2 plus fyy at 1, 2 times y minus 2 squared over 2. Of course, naturally, that's what we do, right? All right, well, now we just start working our way through. In fact, we probably don't need to do everything. We just need to do enough to really narrow things down. So, first off, let's talk about our function. So f, that's our x cosine pi y minus y sine pi x. So, let's plug in x equals 1, y equals 2. So cosine of 2 pi is 1, sine of 2 pi is 0. So we're going to get 1 minus 0. Which means that when it comes to our constant term, our f of 1, 2, this piece right here, we should get 1. Well, there's our constant terms, and we can see, aha, one of these doesn't belong. One of these is not like the other. So that's gone. All right, well, that's good. We've now improved our odds. Instead of having a 1 in 4, 1 in 3. That's great. Now how about our next term? Well, f sub x, you notice they're all the same. So it doesn't really matter what we do. We'll go ahead and do it anyways, just because we're completists. We like to have the whole thing. So take the derivative with respect to x, you get cosine pi y, then minus pi y cosine pi x. So when you plug in 1, 2, what happens? Well, cosine of 2 pi is 1. Cosine of pi is minus 1. So you're going to get a plus 1 from here, minus pi times 2 times minus 1. So now become a plus 2 pi. And you'll see they all agree. Okay, so far, so good. Haven't narrowed anything else down. How about f sub y? Well, what is that? Well, that'll be, come up to a function, take derivative with respect to y. In the first term, we'd have minus x pi sine of pi y. And in the second term, minus sine pi x. All right, now, what happens when, whoops, I forgot my little x. Fy at 1, 2, what will that be? Well, sine of 2 pi and sine of pi are both 0. So we should get 0. Which means that this term here in front of the y minus 2 should be 0. Notice that is not 0. See, there's no y minus 2 term in the last two entries, but there's an entry here at 3 pi, which means we can eliminate option B. Good. Now we have a 50-50 chance. That's pretty good. We've doubled our odds that we'll be able to figure out the right answer. Woohoo! Double, double, double. All right. But wait, we got to keep going. We're not done until we've figured things out. Okay, so let's see. Well, it doesn't really matter what the next one we do is. Let's do f, x, x. So come up here, take the derivative with respect to, here, f sub x. Take the derivative with respect to x. Notice there's no x there. Good. Here, what will happen? Well, derivative of cosine is negative sine. So there's already a negative, so we're going to end up with a positive sign. Notice there's going to be another pi coming out, so that gets us up to pi squared y sine of pi x. Now, when we plug in 1, 2, what will happen? Well, we're going to get a sine of pi, which is 0. What does that tell us? Well, that tells us that the x minus 1 squared term, this piece right here, should be 0, because it's just going to go away. Now, do we see anything with an x minus 1 squared term? We do, right here. And the important thing to note is it's not 0. But of course we already eliminated that, so that doesn't help. The other two options, well, there's no x minus 1 squared. All right, well, we keep going. Sooner or later we'll find something to break it. When I say break it, the tie, not our spirits. Our spirits won't be broken, for we will overcome, and we will not, well, we'll do more than overcome. We're going to love it. Life is good. Fyy, so taking the derivative with respect to y. The second term is going to go away because there's no y. In the first term, the derivative of sine is cosine. And then there's another pi that's going to come out. So minus x pi squared cosine pi y. So Fyy at 1, 2, what will that be? So cosine of 2 pi is 1. So then we get 1, and then minus 1 times pi squared, so that's minus pi squared. So that says that in terms of what should be in front of the y minus 2 squared, we should have a minus pi squared over 2. Notice here we have a minus pi times 2/3, not even close. Minus pi squared times a half. Yeah, good. So again, this part right here, that's, what should be our Fyy. So we can eliminate C. Our odds, they keep improving. We are now down to a 1 out of 1 guess. In fact, multiple choice, we could just stop here and circle it. But we are completist. We want to say, let's go all the way. What is fxy? All right. So it doesn't matter whether you start with fx or fy, you just take the derivative. So the derivative of, say, f sub x with respect to y will be a minus pi sine of pi y. And then here, take the derivative of this with respect to y, minus pi cosine pi x. Okay, so far so good. Looks good to me. So fxy at 1, 2 would be what? Well, we're going to get a sine of 2 pi, which is 0, and then we'll get a cosine of pi, which is negative 1. So we're going to end up with pi. So we should have the coefficient fxy 1, 2 should be pi. Notice a half times 2 pi is in fact pi. So yes, it is D. Final answer. And wow, what a problem. What a problem. Now, don't get too nervous. Again, we'll give you some things which are funner because we want you to have fun. All right. All right. Number 22. The linear approximation of f of xy equals 5xy plus x e to the power 2x plus 3y at negative 3, 2 is one of these. Which one is it? Well, we might even be able to just sort of spot now which one has the right form. So what should be true? Well, linear approximation is tangent line. Notice this has a 2, so you should have a y minus 2. All right, that has a y minus 2. So that's cool. We can eliminate A and C. All right, woohoo! They don't have the right form. Now, what about our other term? Well, we have a negative 3. Okay, so that's x plus 3, x plus 3. All right, so that doesn't really help narrow it down much. So, but now we can kind of see, yeah, it's getting pretty close. It's really going to be the derivative with respect to y. That's going to decide things. So, let's proceed. So what do we have? Well, here's our function. What do we want? Well, we want to know what our function is. So that's 5xy plus x e to the 2x plus 3y. F sub x of x comma y. Well, 5y plus e to the 2x plus 3y plus x times e to the 2x plus 3y times 2. So I'm doing a product rule here plus a chain rule. F sub y of xy would be 5x plus x e to the 2x plus 3y times 3. Now we plug in our points. So our point, negative 3, 2. F at negative 3, 2 is, so we're going to have 5 times negative 3 times 2. So that's negative 30. And then minus 3 times e to the 0, because it's minus 6 plus 6. So that's negative 33. All right, so far, they're both good. Fx at negative 3, 2. What will that turn out to be? Well, that's going to be 5 times 2, which is 10, e to the 0 plus 1 plus negative 3 times 1 times 2, so minus 6. So 10 plus 1 is 11, minus 6 is 5. So that works. All right, and then there's the f sub y at negative 3, 2. What does that turn out to be? Well, 5 times 3, yes? Sorry, 5 times negative 3, negative 15. Then plus x, so minus 3 times 1 times 3. So that's what? Minus 15 minus 9, or negative 24. Aha! That finally differentiates. Good. B. B is the answer. Woohoo! We got one. No, come on. We're doing great. You're doing wonderful. You're wonderful people. You're going to have a lot of fun with this test. Number 23. What is the mass of a wire with density 1 that lies along the curve r of t equals 2 cosine t I plus 2 sine t k, and where time goes from 0 to 1? And this is, again, we're going to try to submit an answer, which is a number rounded to the nearest hundredth. All right. Well, so how do we proceed? Well, what do we have? Well, it's a mass problem, mass of a wire. So the way you find mass is you do the integral along your curve of your density ds. So, in our case, our density is 1. So, we just have to do our ds. All right, so our curve, go from 0 to 1. ds is the square root of the x-coordinate, take the derivative of that, minus 2 sine t squared. The y-coordinate is 0, because that would be in the j direction. Take the derivative of that, it's still 0. Plus, and here, 2 cosine t squared dt. So what do we end up with? Well, we end up with the square root of 4 sine squared plus 4 cosine squared. Well, 4 sine squared plus 4 cosine squared, just pull out a 4, and square root of 4 is 2, and then sine squared plus cosine squared is 1. So that's 2t evaluated from 0 to 1, which is 2. And then, of course, because I'm an engineer at heart, I'll put in some extra precision. 2.00. Ah, our last one. Woohoo! Okay, number 24. Let S be the part of the surface z equals 3x squared plus 3y squared with upward pointing normals lying above R, which consists of x going from 0 to 1, y going from 0 to 1. What is the flux of f of xyz equals xi plus yj plus zk through our surface S? Now, how do you do flux? Well, the flux is really the integral. It's a two-dimensional integral because your surface is a two-dimensional object of f dot n dsa. Now, oftentimes this is hard, but in the special case, when you have z equals a function, you can actually simplify this dramatically. So this becomes the integral over your region R, which is a region in the xy plane, of minus mfx minus nfy plus p dA. So let's simplify and see what we get. So this is the integral over our region minus m. So m here is the x, so minus x. Fx would be 6x minus n, which is the y. Fy would be, take the derivative here, 6y plus p, which is z. But we're doing an xy integral, so I don't want anything with z, but that's okay. Our z becomes 3x squared plus 3y squared. All right. Good? So far? Yeah, that's not so bad. All right. So here we go. Just as a reminder, z. So what do we get? Well, we get that this is equal to the integral over our region. Well, we have minus 6x squared plus 3x squared. So that'll be a minus 3x squared, and then minus 6y squared. Okay, that doesn't sound so bad. Now what's our region? 0 to 1, 0 to 1. Whoops, why did I put minus 6? That's still minus 3. Ha 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 ha. Minus 6 plus 3. Minus 3x squared minus 3y squared. And we'll go dy dx. So, what do we get? 0 to 1. And we get a minus 3x squared y minus y cubed. And we're going from y equals 0 to y equals 1. So that's going to be integral 0 to 1 minus 3x squared minus 1, which becomes minus x cubed minus x from 0 to 1, which is negative 2. That's it. Our last one! What a ride. Thank you for being so patient. It took a little bit longer than I was hoping, but you know what? We got there in the end. And here's the important thing. You can do this. Don't let the problems here make you nervous. We don't want you to be nervous. We know you've learned the material. We know you've done great. The class this semester has been doing a great job, and you can do a great job on the final. And I think this might be our farewell parting words. So thank you for being a part of Calculus. We hope you've enjoyed it, and good luck on the exam. All right. Bye.